Our first speaker after 3 years is Kalavri. Vasia is an assistant professor at Boston University, and she has the great pleasure of starting her career just when COVID hit. So, it's 3 years of dealing with COVID at the beginning of her career is not the ideal thing to do, but she's here. Vasia got her PhD from KTH and UC Leuven, and then spent some years at ETH and as a postdoc, and then came to Boston U. I know of her work primarily in the domain of streaming data and also graph processing, but I think she's going to talk about different things this time. So I'll leave it to Vasia.
Sure. Okay. Thank you very much. Can you hear me? Okay. Yeah. Okay, great. Yeah, it's wonderful to be here. Thank you very much for the invitation, and thank you very much for hosting me. So indeed, I know some of you, Sami and Tamer and Kuzaima, since I was a PhD student, really working on graph data management and stream data management. And I guess my connection to you all is because of these topics. But what I'm going to talk about today is something quite different. It's also a new direction for me, but hopefully it's going to be another reason to connect with you. And really, as I was telling Tamer before, this is a project that I started during the pandemic. So it's my pandemic project, which turned into actually one of the big research directions now in my lab. So let me just start with defining a little bit what I mean by collaborative analytics and give you some idea of the use cases that motivate this work. So consider a set of data owners who want to perform some computation on their collective private data without revealing this data to anybody, right? And without revealing the data to each other either, right? And these data owners could be, for example, healthcare providers like hospitals or medical investigators who might want to do a study on the union of the databases of their patients, right, for the greater good. Or it could be companies who might have agreed to provide their employee salary data for studying the gender or racial wage gap, but only if this employee data is not revealed to anybody so they don't lose their advantage, right? But for the social good, they say, okay, you can query my data. You can only learn the result of this query. If you don't learn anything else, I'm fine with it, right? Or it could be end users like us who might be willing to provide their data to companies, maybe advertising companies, in turn for good recommendation algorithms. But at the same time, we don't want these advertising companies to learn anything about our data, right? So this is the class of use cases that motivate this work. We call this collaborative analytics because we have a set of data owners, right? And a query that we want to run on the collection of this private data, right? Now, I guess it will not come as a surprise to any of you that security is expensive, right? If I want to do a query on a private data without revealing anything, that is going to be really, really slow. And just to give you an idea of how slow it might be, I just selected a couple of results from recent papers. One is from a systems paper and one is from a database venue that show just how little we can scale if we run a query end-to-end secure. So really both these systems, what they show is that if you want to reveal nothing, right? This is what I call no leakage. You don't want to reveal access patterns. You don't want to reveal the original data, nothing, just the end result. Then you can only scale in reasonable time to a few thousand records, really, right? It's really slow to go beyond that, right? So this is just as a, I'm just bringing these results here just to have something in mind of how slow we're talking about. But of course, there has been a lot of work in our community in exploiting this trade-off between security and performance. Really the idea being that, okay, what if I can leak a little bit, right? How much performance can I get by leaking, let's say, the intermediate result size? Or how much performance can I get if I leak the access patterns, right? So here I categorize 3 main approaches that I place under this security performance trade-off direction. The first one is information leakage. So if I can leak access patterns, or if I can leak intermediate results to some untrusted parties, either without noise or with, right? So I can even protect what I'm leaking, right? Then I could gain some performance, and I can scale much beyond the 1,000 records that I showed. Another line of work is leveraging physically protected hardware, right? So this is not really leakage, but it is a security performance trade-off in a sense, because you are trusting the hardware to be secure, right? So this idea says that I'm going to compute on plain text data inside an enclave, right? Or I'm going to push some of the computation to a trusted local resource, right? So in this example that I said before, if the data owner has some computing resources that are local and are trusted, maybe they could run part of the query locally, right? And then we can run the rest of the query collectively in a secure manner, right? And this way, again, I can scale to much larger data sets. Yes, of course.
So theoretical results would say that it's not possible to answer these kinds of queries efficiently without thinking.
No. No, so actually, this is exactly the point of my talk today. I want to show you that it is possible, even though we thought it's not. If we rethink about the software stack that runs these queries, and if we actually take a clean slate approach and understand how these computations are performed, then we can scale to much, much larger inputs. There are theoretical results that give you the complexity of these computations, of course. I will come to that. But with our new hardware and our understanding of distributed systems and systems in general, systems optimizations and database optimizations, we can indeed scale to much larger inputs, right? That's exactly what I want to convince you today, that it is possible. And yeah, feel free to interrupt me if any questions. Thank you. All right, so yes, so these are the common approaches, but the issue is these are not always an option. At least when we started working in this area and we discussed with potential users like hospitals in the Boston area or companies like Red Hat and Bosch, who are now our collaborators, basically they told us even the minimal leakage is a no-go, right? We cannot leak anything, right? There are investigators at BU that I know of who cannot share their patient-sensitive data even with their collaborators on their grant if they're not a BU employee, right? So they have collaborators at MIT, for example, they cannot share the data because it's so sensitive, right? So sometimes even the very little leakage is not good enough. And just to show you a couple of examples of what this leakage might reveal, right? There's a lot of research in this area. I will not go into details here, but let's say, think of this example of the gender wage gap, right? And let's say one of the intermediate queries that we want to run in this analysis asks for women managers with a salary above some amount, right? If we reveal the result of this, the result size of this query, right? Not the result, but just the size, just because the women managers are so few, right? We might be revealing identifying information about these people, right? the same holds with revealing access patterns, right? So let's say I'm willing to reveal the access pattern. So for instance, how often do I take a branch? Like how often does is a condition true, right? This might potentially reveal which of the participating companies are contributing the most to the wage gap, right? We don't want that, right? So this is what I mean by no leakage is we hide the data, we hide the result sizes, we also hide the access patterns, we hide everything. Make sense? Okay. So this is in terms of the first approach that I showed. When it comes to hardware-based solutions, again, there is a very large body of research that shows we can hack hardware, right? Or we can attack hardware, right? So there are many side channel attacks that might leak information when you're using enclaves. And the third kind of approach, pushing the computation or part of the computation to the data owners, sometimes is also not an option. For instance, again, the hospitals we're talking to, they don't really have the IT infrastructure or the expertise, like their employees don't know how to set up secure computation, right? So ideally, we would like good performance, right, with provable security guarantees, no leakage in the outsource setting, right? So this is exactly the setting that I'm going to talk about, right? We want this as a service, right? Without relying on any trusted resource. And this is what we're building, BU, we call this system secrecy. It's a framework that supports collaborative analytics in untrusted clouds. So you don't have to trust the cloud providers. That's what I mean by untrusted. And it has no leakage at all, no reliance on any trusted resources, and it can support complex SQL queries. Yes. Mm-hmm. Yes, that's a great question. So I have a slide on the threat model in a bit, but this is very important. I'm not talking about hiding the result of the query, right? I'm talking about hiding the input data, the access patterns, and the intermediate result sizes. So the query is public, right? And usually the data owners will agree on the query before giving their data. Like, for example, companies want to participate in the wage gap study, and they know that the output of that analysis will be, let's say, the wage gap. How much is the wage gap, right? Nothing else. But I'm not talking about hiding the wage gap itself, right? I'm not talking about hiding or noising the result of the query, right? So this is more a differential privacy kind of approach. I'm talking about hiding the input data and anything related to the computation while the query is executed. Yes. Yeah. Yes. I'm going to give the result to the data analyst, right? Not necessarily to the input parties and not to the computing parties. No. No, so the technique I'm going to be using here, the cryptographic protocols I'm using, do not protect anything that can be inferred. So if you make several queries, right, then you can infer things about the original data. Yes, I'm not protecting against that. Yes. Yeah. Yes. Right. So there is a provable guarantee that you don't leak, you only reveal the result to the designated querier, right? And everybody has agreed before that this is going to happen, right? But you don't leak anything about the input data or intermediate computation. Makes sense? Okay. Yes. The size of the output will be revealed, yes, because the output is, well, it will be revealed to the analyst. Yes, absolutely. Yes.
Yeah, so you mentioned that queries for the cloud then goes to the data analyst. So what role does the data analyst play?
I'll show you in a bit.
That's okay.
Yes. These are great questions. All right, let me give you a bit of a better understanding of the setting, right? So we have a set of data owners, the hospitals, the companies, or us, right? And we are using secure multi-party computation. This is a family of cryptographic protocols that allow distrusting parties to compute any arbitrary function on the collection of their data, right, without revealing anything to the other data owners or to the computing parties. And the way this works, I'm going to show you an example, but I'm just going to give you a very high-level idea now, is that the data owners split their data into random strings. They encrypt, in a sense, their data into random numbers that they distribute to computing parties. So I'm using the distributed trust setting. This is what this means. So I have, in the case of secrecy, 3, but it could be any, computing parties that are in different trust domains. So you can think of those being 3 different cloud providers, for instance, right? That are non-colluding, and then they will follow a distributed protocol. They will compute on the random numbers and generate shares of the result. They will generate some random numbers that if we put together, we will reconstruct the result of the query, okay? So this could be, as I said, competing cloud providers or resources managed by different entities in a federated cloud. So if, for instance, the hospitals do have local resources, they could build a federation among themselves, for instance, okay? So now the way secrecy works is we provide this as a service. So you have the data analysts, right? So this could be, let's say, the medical investigator who wants to run the medical study, right? Or the city of Boston who wants to know the wage gap. This is actually a real use case of MPC. The city of Boston is using MPC to compute the wage gap. So this is the data analyst, right? And on the other side, you have the data owners who provide their private data for this specific computation, right? So they have agreed to this specific query, right? And they know that the only thing that the analyst will learn is the output of this specific query. Make sense? So the analysts submit the query to our service. Our service deploys the computing parties. In the case of secrecy, we use 3 computing parties on possibly different cloud providers. Then the data owners secret share their data. So they do this random number generation and encryption of their data, send their PCs to the computing parties. The computing parties will follow their protocol, possibly over the internet. And once they're done, they will send back pieces of the result, right? So essentially random looking numbers that the analyst can then put together and reconstruct the output of that specific query. Make sense so far, the setting? Yeah. Yes.
Data owners who supply a table somehow
Yes.
bringing all the content.
I will show you exactly what they do. Essentially, they take each value in their table and split it, and not split it, transform it into, in this case, 3 random numbers that if you put together in one way or another, that I will show you in a bit, they reconstruct the original data, but on their own, they're just random numbers, so they mean nothing. Make sense? Yeah. Yes.
The office here is very much include the data on the data. So security systems depend on data. Like if data on the screen, sign off on that query, despite the secret sharing scheme, it's still possible to
So you mean having a malicious analyst that sends another query in the end?
Same query, but it's just that they have obfuscated it so much that it's hard for data owners to understand what exactly the query is doing. So they think that it's there, but
Right. So if they know what the result of the query will be, then that's enough. It's not about how the query will be executed, right? Because this is all hidden. It's about the end result. So if the data owners can understand what the end result will be, what the result will be, then it doesn't matter how we execute the query. Is this what you're saying?
I'm saying that for the data owners, thinking that there is there. But when it's actually, and they might get access.
Yeah, so the data owners can disagree. Like they don't have to provide their data in that case. That's true. But, sorry, excuse me. But then because the query is public, there are protocols who can add an extra layer of security and make sure that it is indeed the query we agreed on that we're computing. I'm not gonna show this now, but it is possible, yes.
So two quick clarifications. So I got another scheme, right?
Yes, exactly. So there is a public catalog at the secrecy service. Yes,
Your model is one shot query. So
yes.
there is put together lots of information from the query to how to just.
No. So the data owners will have to agree on each and every query. So if you want to run another query, you have to again get their agreement. Make sense?
Fundamental assumption that data analysts are malicious.
Yes,
Data
yes.
analyst is going to run the query that they understand.
Right. The query will, yeah, the data analyst will submit the query, right, to the secrecy service. The secrecy service will ask the data owners, do you agree on this query? And it will deploy the protocol on the data parties, right? The data analyst is not involved in the query processing, just submitting the query. Make sense? Great. All right. Awesome. So yeah, here's the third model a little bit more formalized. So what we follow in this work is called the semi-honest model. So our assumption is that parties, the computing parties, will not deviate from the protocol. So they're honest, but they're curious. So they can try to figure out what the data is. They can try to reconstruct. They won't be able to with provable guarantees. And we also allow one adversary who can take full control of one of the three parties, and they can also monitor the network, and they can see access patterns and everything, but not alter its execution, right? So we allow a passive adversary who can look at all messages being exchanged from one party and all computation happening in one party, and they still won't be able to understand anything. So essentially, what that means in practice is that if at least two of the three parties are honest, then we provide provable guarantees. All right. And under this threat model, we have provable guarantees that the untrusted parties will not learn anything about the original data, the intermediate result sizes, the data access patterns during the query execution. Okay, there are stronger protocols than this, right? You can also have an MPC protocol that can also check the integrity of the result, right? In our case, we assume that the parties will follow the protocol. Yes. Yeah.
Yeah, within that select salary first spread.
Yeah.
And I guess this is the query that the data providers would not.
Yes.
It's caught there. Data providers.
Mm-hmm. Right. Yes. You could also have more advanced agreement protocols. For instance, one use case that I know of from the medical sector says, I'm going to provide my data, but only if there are at least K participants from each other data owner, right? So you could do such checks as well. Okay. Yes.
these honest compute messages, are they data owners and compute owners and data owners? They can all be honest compute or?
No, so here I'm talking specifically about the computing parties, those that compute the protocol. So the three in the middle here, the cloud providers in our case. Yep. Yes. Yeah. Yes. Yes. Exactly. Exactly, yes. So I'm going to show you in a bit because two parties, if they collaborate, they can reconstruct the result, but one on its own cannot. This is why we have one. Yes, so there are different types of protocols. You could have two-party protocols with one adversary, three-party protocols with 2 out of 3, and so on. So this is an K out of N type. So this is specific to the protocol we're using in secrecy. Okay, okay, I'm gonna move on. All right, so let me show you how that works with an example, all right? So very simple example for now, we just want to compute an addition, right? So I have two data owners, they each have a number, 5 and 4, and I want to securely compute the result of 5 plus 4, right? So what they're gonna do is split 5 into 3 random numbers, random shares, we call them, that if you add them up, they give you the original number, but on their own, they mean nothing, right? They're just random numbers. So both of them do the same, right? They split their data into these random shares, and they send their shares to the parties. So in this specific protocol we're using, this one here, each party receives 2 out of 3 shares. That's why one party cannot reconstruct, but 2 of them, if they collude, they will be able to reconstruct the original data, all right? So each of them has 2 shares of its input. And then, very easy, they get the public query, which is just an addition here, and they can just locally add their shares, right? And if they add their shares locally, they will end up with 2 shares of the result, right? So each party again just sees some random numbers. They know nothing about the result, right? But if they send their shares to the analyst can put this together and they will get the result 9. Make sense? Okay. So addition is easy. Let's do a multiplication next, right? So here again, 5 and 4, I want to compute 5 times 4. Same thing, I have sent, its data owner has sent 2 shares, 2 random shares in each of the parties. And the parties need to compute this formula here. If I rearrange it a little bit, you will see that again, they can locally compute these 3 terms, M1, M2, and M3, right? And they will end up, in this case, with 1 share of the result, right? Now, if I want to use this in a subsequent computation, they will have to perform 1 round of communication, right? And send their second share to the other party in the ring. So in the end, they end up with 2 shares of the result. Make sense? So in the addition, with just a local operation, they end up with 2 shares of the result, which means they can take these shares and input them to another addition or to another multiplication, right? And here I needed 1 round of communication to exchange my second share. And again, they can use now this secret result as an input to another operation, right? And this is how I can chain together additions and multiplications and build more complex operations. Make sense? Okay. So what I just showed is called arithmetic sharing. So the idea is that we split its data item into 3 random numbers that if I add up, they give me the original number. But we can also do Boolean sharing with XORing the bit representations. And I have the corresponding primitive operations. So I can have addition, multiplication on arithmetic shares, and I can have XOR and logical AND on Boolean shares. And on top of these primitives, we build and we can build protocols for more complex operations. So I can use XOR and logical AND to build equality operation between two numbers or between two columns of a table, or inequality, or I can convert from one to the other representation, or I could build a compare and swap operation. And then on top of these primitives, I can then build relational operators, right? So we have select, distinct, group by, join, semi-join, order by, and composition of these operators. Okay, great. So
Building a virtual machine.
well, yes, kind of a secure one. Yes, so we did. So coming back to what I said in the beginning, this is how I spent my lockdown, right? Building this from scratch, really from scratch, from 0 lines of code. And there is a reason why we did this, because we wanted to understand how these protocols work so we can optimize them, right? So exactly to see whether we can challenge this idea that we can only scale to a few thousand rows, right? And so we build all of this from scratch. I will just show you a little bit how the higher level primitives work, right? So addition, multiplication, I think you got the idea, right? But let's say we want to build something more complicated, like an inequality, right? The whole concept is that you have to build everything in an oblivious way, right? So you cannot have access patterns that depend on input data. You cannot have if statements, selection statements. You cannot have any data reduction, right? So your result cannot be smaller than your input, the intermediate result, right? Otherwise, you're revealing information. So everything has to be data independent. So for instance, let's say I want to do A greater than B, just an inequality. How do I do this with multiplications or XORs and logical ANDs? It really boils down to a Boolean formula, most of the case, that most of the time that takes the binary representations of my shares. And in a naive protocol, what it would do would be to compare bit by bit, the most significant bit, second most significant bit, and so on, one by one. And I would end up with a secret share of a bit, where 1 would mean A is greater than B, 0 would mean A is not greater than B. All right? Now, if I have this, I can build selection, right? I could compute a query that says, is salary greater than some number, right? All I have to do is compute this formula for each of the elements in my table, and then I would end up with a new column of a secret shared bit that tells me whether this is in the selection result or not. Make sense?
What's the encoding of text do though?
What do you mean?
So
Sorry.
You'll have to have a binary like an ASCII representation for text, and you're gonna do the same thing for string equality comparisons and everything?
Right. So we don't do string comparisons yet. So everything is integers for now.
Okay.
This is a very interesting direction for future work, and I have a use case that we're working on.
So you can't select row of Fred, right? Even you don't want to, but
Yes,
you can't do it
yes.
right now.
No. So this is all for integers for now, what I'm talking about. Yes. Yes.
First order SQL, the rewrite their word.
Mm-hmm.
Is that all second enough, or you have to do some fixed point stuff?
So right now we don't support fixed point. No. If that answers your question, yeah.
This one, so this concept around comparison, right? They don't send the salary data to, they send row 1 to 1 or row 2 to 1.
Yes. Exactly. Yes. So here you could think that these are like 3 different data owners that have sent shares of this to the three parties, and the parties compute that Boolean formula that I showed, and they end up with secret shares of this phi column, right? So again, these look like random numbers to the parties, but if you put them together, this will reconstruct 0, 0, 1. Make sense? Okay, great. So really, the reason why we went into all this trouble, it might sound trouble, but it was really fun building something from scratch. It was so that we could open the black box of MPC, because really in the most of the works we had looked into before this, and most of the libraries that we had tried to use, they followed an approach where they considered MPC as a black box, right? So I have this secure computation library here, like I have my query on the other side. I will do whatever optimization I can or push computations maybe to the data owners. And then for the secure part, I'm going to use this MPC black box to compute it, right? And that is, I guess, easy or simple, like to put together. But on the other hand, it doesn't allow you to do any optimization inside this MPC library, right? So really the approach we are following with secrecy is building an end-to-end secure MPC query engine where we can optimize the query under MPC, which I'll show you in a little bit. All right. So, sorry. So the core ideas behind secrecy that make this possible is really a careful redesign of all the layers, from the primitives to the relational operators to the optimizer that optimizes the query. And the first thing that makes this possible is that we redesigned these MPC primitives that I showed to work on relations, directly on relations. So if you take an off-the-shelf MPC library right now, it's not built for working on relations of things, it's built on working on pairs of elements. And I'm going to show you in a bit why this is super, super, super slow, right? So with redesigning these MPC primitives, we could amortize the network IO, which is our main cost in MPC, and make secret sharing competitive in one environment. So this is a very surprising result, at least to our cryptography colleagues, because they most of the results show that this technique I showed you, the secret sharing, because it has these rounds of communications, doesn't work in a wide area network. But I'll show you that it does if we do message batching. So very simple example. Again, we have this inequality primitive, and I want to compute a join between two tables, R and S, right? Where A greater or equal to B on the S table, right? So if I do this naively, or if I do this with one of the off-the-shelf MPC libraries, what I'm going to end up doing is computing this Boolean formula for each and every pair of A and B. And to give you an idea in terms of computation, what that means, all these blue XOR operations are local operations, right? So they're like the addition that I showed you. The parties can compute this locally, right? So no communication here. But all these logical AND operations, these are multiplications, right? That, like the multiplication I showed you. So each one of these require one round of communication, right? So imagine if I did this in a naive way where I communicate one element for every single multiplication, right? So essentially what we did is very simple. We batch all these elements, all these messages together into one big round of communication, right? So in the end, the communication rounds of the join operation don't even depend on the length of the input, right? They're only dependent on the representation length of our numbers. This is the L here. So I only need log L plus 1 communication rounds in total to compute the entire join. Make sense? All right. Now, in practice, this has a really surprising result. So most of the relational analytics frameworks that used MPC before secrecy, they didn't use secret sharing. They used another MPC technique that is called garbling circuits, exactly because this other type of protocols, they have constant rounds of communication. So secret sharing has been thought of as not fit for the wide area network. But essentially what we see with message batching, and here I just show you some results for join and sort, two operators with increasing inputs, and the light blue is local area network, the dark blue is wide area network. The overhead is really small when we go from local to wide area network, and it gets smaller as we increase the input, at least for sorting, right? This was very surprising. So batching amortizes the communication cost of MPC and can make secret sharing really competitive in high latency WAN environments. The second idea behind secrecy is the modeling of operation, communication, and composition costs. So essentially, we build a cost model of the relational operators in terms of these three types of costs, right? So how much computation you do locally, how many rounds you actually need to perform, and what is the extra cost of composing these operators, right? So I showed you the selection before, right? But if I have another selection after it, I will end up with two columns of these secret shared bits. If I need to compose them, right, I also need an extra logical end, right, to get the result of these two. So composing different operators has different patterns, and it has like an extra cost. And the interesting thing here is that if you go and apply plain text optimizations on MPC queries, they don't always work. And I'll just show you a very simple example that you might be thinking already. So let's say I have a join and a filter. Plain text optimizer would never really execute it this way, right? They would push the filters down. This is rule number one, push filters down, right? But in MPC, really, this doesn't make any difference at all, right? Because remember, I do not reduce my input data. My filter will just add a new column in my table, right? So it really doesn't make any difference to push filters down. So when we started looking into this, we were thinking, okay, maybe we don't need to do any reordering, or no optimization can work under MPC. But that's not true. There are still some reorderings and some transformations that make sense under MPC. So we looked into these transformations, and based on the cost analysis we did, we came up with a set of optimization rules that you can still apply under MPC and get really good performance. I'll just show you a couple of them. So let's say we have a join and then a distinct, right? So in terms of cost under MPC with the specific protocol I'm using, this would be n square log square n operations or messages, and log square n rounds, and n square space. And the reason is because I would need to materialize the output of the join before applying the distinct, right? And because I cannot reduce the output of my join, I will have n square output, right? However, if I push the distinct down, I can bring my space down to n, right? Because I can now compute my distinct first and then my join in a pipeline manner. I can reduce my rounds by 4 times, and I can reduce my operations and messages as well. And this might not seem like a huge reduction, but in practice, this is more than 100x improvement for 1,000 rows, right? So just to show you a little bit a result here, this is a query, the same query that I showed, distinct push down, the naive version or the baseline version, and the optimized version. And you can see that the naive version cannot even scale to more than a few thousand rows. Yes.
So just a quick commentary. So I don't think it's about whether or not an optimization is applicable or not. It's more about the fact that the cost models just.
Absolutely. Yes, 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 absolutely. So the all valid transformations in plain text queries are also valid here, right? It's just that the costs are different. Exactly. Absolutely.
Makes some sense to these.
Exactly, exactly. Yes. So these are all valid transformations. All the transformations we already know. The same ones are applicable here. It's just that the costs are very different. And actually, the interesting part is that the costs are exact. So we don't need to do any estimation because we know exactly what is the output of every operator, right? So it's much easier to build an optimizer under MPC, really.
So things like selectivity estimation. Just
Yes,
completely irrelevant.
exactly, exactly. Yes. Yes. So it makes sense to push down blocking operations like sorting and group by and distinct as you can, as much as you can, and push up join operations. Because that reduces, I mean, the goal of reducing your intermediate result sizes is still a goal here, right? If you think about all the operations under MPC, the only one that increases the intermediate size is the join. So if you can leave the join for the very end, that will give you a benefit most of the time. And if you can push the sorting to the input, your input is really the smallest data set that you will have during your query, right? And sorting is the most expensive operation here other than join. So if you can sort the input, then this is probably the best you can do. So this is intuition. We haven't exhaustively found all optimizations that exist. These are just a few that we have come up with that I'll show you, but I think this is the general principle. And then you can go into questions of, do you want to reduce a number of rounds or do you want to reduce number of messages? So if you put into if you also consider the dimension of network and cost, cloud cost, right? Then I think you could build a multi-objective optimizer, right? That also decides the operator or the query based on your network latency or the cost of where your parties are deployed. Next step, but yeah. Yes. Yes. So the distinct is based on sorting, this particular one, right? So the distinct will sort the input with which in its input, which in this size is n, while in that case it's n squared. This is where the most of the benefit comes from. No, so the distinct does not increase the size. Yes, it will be the same. It will be n. The output of the distinct will also be n size. Make sense? Yes. Sorry, can you repeat? Yes. Yes, absolutely. So if you have multiple joins without any knowledge about foreign key or primary key, so you cannot do anything better than n squared, right? You will hit a wall sooner or later, right? There are optimizations you can do if you know if you have knowledge about foreign keys or primary keys, and if you have aggregations after your joins. But in this case, and in secrecy, in this version of secrecy, we assume a nested loop join. Okay.
And I wonder if you can provide any You don't have any money at each level. So I'm also wondering if you have anything on your mind that you can apply for this particular
So we have we are working on a version of secrecy that does multi-way join optimization, but this is only taking into account foreign key primary key relations and aggregations after the join, which is really the most common query under MPC. So you cannot really imagine, so you could have queries like this, where the output is the distinct of something, or it's the aggregation of something. But under MPC, you will never open the entire join output, right? So in these cases, the best you can do is bounded by the output of your join tree, right? By the maximum output of your join tree. I don't know if there are protocols that actually respect those bounds, but at least this is my understanding, is that this is the theoretical bound that you have. Okay, I'll move on because, yeah, okay. I have a few more slides. So what time do we have to finish? Oh, okay, so then I have to go really, really fast. All right, maybe I will skip this, but there are other optimizations and transformations you can do, pushing down, pushing up, or decomposing operations. This is another one. So in our paper that I will share in a bit, we did this cost analysis, and we also build an optimizer that applies these optimizations automatically on vectorized MPC execution. And other than the logical optimizations that I showed you, we have a series of physical and protocol-specific optimizations as well. I don't have time to go into them, but I can talk to you if you're interested. Sorry, I have to plug in, apparently, my laptop. Okay. Just want to show you a few results, right? Going back to okay. All right, so this plot shows a set of queries that we ran, including some TPC-H queries. And these are queries that were used in prior MPC works that do different types of analysis, medical queries, and these are some business analytics queries. And the gray bar is baseline, not any of these optimizations that I showed. The red line is secrecy optimized, but the gray line also has batching. So if we don't use batching, we cannot scale to more than a few hundreds or thousands of results. So the baseline also uses batching so that we can compare something meaningful. So what we saw is that logical and systems optimizations result into even 3 orders of magnitude speedups for some queries. Protocol-specific optimizations up to 20x. These are for small inputs, just to show you a little bit the effect of these optimizations. And this is a one experiment in 3 different regions in AWS, 2 on the East Coast and 1 on the West Coast. So this is, the part is communicating over the internet. We also compared with one other MPC library, which is called EMP. And I'm going to show these results with an asterisk because EMP uses a different MPC protocol. So the protocols are not really comparable. They have a different model. They only have 2 parties and garbled circuits. But I think the comparison can give us some intuition because EMP has been adopted by all relational MPC frameworks, right? So if you're going to use MPC, secure MPC, there's going to be EMP underneath, right? So this is secrecy versus EMP on a join. And here, really, EMP needs more than 11 hours for 40K rows per input and really couldn't work on larger inputs, while secrecy completed the join in less than 4 hours for 100K rows per input. And in terms of sorting, similarly, secrecy can scale to much larger inputs, 4 million rows here in 42 minutes, while EMP ran for over 9 hours in the same setting. Now, if we look at queries, there are different types of queries and different scaling behaviors. TPC-HQ6 is an easy query for secrecy. It only has selections and global aggregation. So 5 selections and global aggregation. Secrecy can scale to millions of rows in a few seconds. It's great if you think about the results that I showed you in the beginning. And here is a set of much more complex queries with group bias aggregations and semi-joins. Again, secrecy can scale to millions of rows. It needs a few hours, but at least it's possible, right? And well, 1 hour for 2 million rows. And if this still doesn't sound very impressive to you, I have a secret to share that all of these results are with a single thread per party and just 32 gigabytes of memory. So really what we have been doing over the past few months is parallelizing these computations. And because our distinct group by and really the most expensive operations, joins as well, are sort-based, we have been parallelizing our sorting, very preliminary results, but really we can bring down sorting of 2 million rows to a few seconds, right, in the wide area network, which is great. I mean, we're gonna go from hours that I showed you now to a few minutes. I'm like super excited about this. Yes. So this is again 3 parties, so 3 machines just multi-threaded within each party. But yes, collectively, right, under MPC. But again, only 3 parties, so 3 machines with 32 threads each. You could scale that to having a cluster per party as well, right? So you could go further, for sure. Okay, so I will conclude with a couple of use cases that we're working on right now. One is in collaboration with BU Medical and the Hariri Institute for Computing. They have been looking into secrecy for digital health analytics for vulnerable populations. So the idea here is having patients with wearable devices and then using their data to understand their collective behavior, like of the cohort, and make recommendations to them based on their health. And the second one is very interesting and goes back to the string processing, string matching question before. It's a use case that we got from Red Hat. And Red Hat has OpenShift, right? So they provide OpenShift, which is a version of Kubernetes that they provide support for, right? So a cluster management software. And they have many clients that run OpenShift in their clusters, right? And Red Hat wants to be able to monitor the behavior of OpenShift across their clients, across their clusters, to prioritize bug fixing, for instance, right? Or to understand critical issues that happen across clients. And right now, because the client logs are very sensitive, they have to go through a very, very long process of lawyers and agreements and de-anonymization of the logs and so on. So it's not that they cannot do this at all, but they hope that with secrecy, they're gonna do this really more easily, right? And the idea would be that the clients provide either continuously or in an ad hoc manner secret shares of their logs to secrecy, and then the Red Hat engineers can directly query the logs for incidents or bugs that are frequent across many clients. So we are working on a demo on this. I think we'll have it ready really soon. We're working on a bunch of other things. Because I'm running out of time, I just want to say that this is a collective effort. John and I started this and Mayank during the pandemic, but we're a much larger team now. So Mohammed is my PhD student. He's great. He rewrote all of my code and made it go really, really faster. He's really outsmarted me. And, you know, what I thought was possible now, I think it's totally possible because I have Mohammed on my side. And then we have a few other students who are working on this. We have a paper that is coming up at NSDI 23. You can find the camera ready in this link. I guess I will share the slides. We're hiring students and postdocs. If you know anybody who's interested in this area, please have them talk to me. Yes, and that's, thank you. And that's our new data science building. We're gonna move in the end of December. So yes, I put this on purpose there to, you know, attract people. So computer science, I think, will be somewhere in the middle. So we'll have good enough view of the Charles and the Boston skyline. All right, and with that, that's it. Thank you. Sorry, I haven't been monitoring Zoom. I wonder if. Okay. Yeah. Okay. Yes. So if an adversary compromises a party, so this is an assumption, right? Yes, yes. So under this assumption, we offer these guarantees, right? So if the adversary altered the execution, then this doesn't work. Yes.
On the trade processing time. But you don't have the basic protocol by yourself. How much it will affect the trade processing time?
So which layer are you talking about? Yes. Yes. So we call the system secrecy. Right.
It might require some extra computation given that this is right? And I was wondering if you will measure such time.
So are you talking about that secrecy over there? I'm trying to understand which layer.
The baseline to attribute is NPC.
Yes.
If you're not doing secure, then it's not a baseline.
Exactly.
If you're doing baseline is NPC, then I think your data of NPC standard is black box.
Right.
Only on the
Exactly. So our right.
So that's the baseline. Otherwise, no security baseline.
Yes, exactly. Exactly. Yes. So yeah, it doesn't make sense to compare with plain text query processing if this is what you're asking, right? Because you don't provide any guarantees with plain text. Of course, there's going to be an overhead. It's a huge overhead, right? But here, this is more about making something possible, right? That wasn't possible before. And even a few hours of execution is better than not being able to share your data with your collaborator across the river because, you know, there is no legal framework to do that. If that answers your question, right? So we're trying to optimize this execution and make it faster, right? But without leaking anything, right? So the baseline is an MPC library or something else that would not be optimized for relational queries.
Okay, those are the burning questions. So thank
Yes.
you.
Thank you.